www.nanohub.org.
You can follow along with this presentation using printed slides from the NanoHUB. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
So in the last lecture we talked about spin, and what I'd like to do is continue but touch on a slightly different aspect. Now with spin, the point I was trying to get across is that there is a very different issues involved when you get to non-collinear spins and collinear spins, right? Because collinear spins you can think just as red and blue. And so what I'll be talking about now in this lecture, you could more or less, basically we'll assume collinear spins. So in that sense, the extra complication due to non-collinear, those issues are not involved. But the way it is a little more complicated is it kind of involves the two topics together, namely heat flow and spin flow. What I mean by that, like the last lecture, yesterday I talked about heat flow, and then today we talked about spin. And here I kind of consider the two things together and some of the very important issues that one should be aware of. Okay, and that's why I kind of wrote here, again for your reference, the equations we had for heat flow, if you remember. The way we talked about this was that, well, if you have these electrons, and for this discussion, let's say, at some level here, and as we discussed, whenever an electron goes through in this elastic resistor model, you can calculate the current from this equation. We have written this conductance in various forms. One of those is this one. So number of modes, mean free path, etc. And if you wanted to write heat current, it almost follows from here. Only thing is, instead of the Q, you have to put in this E minus mu. That was the idea. And the idea being that when an electron comes in from here, and if you think of an electron going through an energy channel at some energy E, then the amount of what the electron that actually comes into the contact has an energy mu1. What is here is E, and it essentially picks up that much energy from the contact. So that's how you look at the heat current. And then what it dumps there. And if you looked at the overall heat current, the conservation of energy would be something like this. This is the heat you take from, the way I'm defining my heat currents is that if it's positive, it means it's coming from the contacts. So this is what you get from the contacts. This is what you get from the IQ2. And this is the part that's coming from the battery, etc. Right? I think this is what we had discussed. Now, we'll come back to this. Now, getting back then to the spin valve, I want to use it as sort of as an example to show that there are problems where even in a nanoscale device, you may not be able to write the current this way as F1 minus F2 times something. This was kind of a central thing, that no matter what, you can write it as F1 minus F2 times something. And that's something then we can talk about what it looks like in different conditions, right? Now, so the example we are considering is the following. So just the spin valve we discussed before, but now let's assume that the channel has lots of these paramagnetic impurities, manganese impurities. So what do these impurities do? Well, they give you lots of spin flip, basically. Why? Because there are all these impurities which can be either in an up state or in a down state. So left to themselves, there's one electron in there, there's an up state or a down state, but you cannot put two electrons in it because of this kind of Coulomb blockade type situation that takes too much charging energy to have two in there. But it could be either this or that. And so as long as the chemical potential is in a certain regime, this is the state it would be. It would either be this or that. And so there would always be an unbalanced spin. It would be, so these are what are called paramagnetic impurities. And there are lots of defects in different semiconductors, and in gallium arsenide, the experiments we have done on this, those involve manganese impurities. So there are different things that would give you this kind of a situation. And that's what I've indicated there as those red and blue dots. And I say red and blue because you see half of them are upspin, half of them are downspin. Left to themselves, there's no energy difference. It could be in either place, and left to themselves, it will be 50-50. So that's what I've shown there. Now, how would you model that? Well, in our resistor style model, that would appear as a major, like a spin flip conductance here. That basically kind of shorts the two channels together. In a sense, if you have a lot more ups, it will send a spin flip current and do it. And of course, normally if you're building a spin valve, no one in his right mind would do this. They go to great lengths to avoid this. You're trying to get rid of all magnetic impurities, right? But here I'm really trying to make a conceptual point, which is what I'm saying, let's do. So let's say we got lots of these impurities. And the way you then model it often is you think that, well, the impurities are half and half red, half blue. And so this is how I model it. That's the resistor. And the way you often calculate, how do you calculate the current in this case? Well, for this discussion, let's assume we have very good contacts. So in a way, as if this is just open. So very good spintronic contacts. So only these reds come in, blues get out there. That's it. And these are anti-parallel, of course. I'm taking the anti-parallel configuration, okay, for this discussion. And so what would happen then is, you see, if you didn't have this spin flip thing, there would be no current at all in such a circuit, because this is the anti-parallel thing. This would be like having infinite magnetoresistance. Parallel, great conduction, anti-parallel doesn't work at all. Okay. But then, as soon as you allow some spin flips here, then current can flow like this. Okay. So the question is, how would you calculate that current? Okay? Because here, this approach isn't quite getting you there, because here, that is based on conduction through up channel, conduction through down channel. But here it is different. It's like up channel by itself doesn't conduct too well. Down channel by itself doesn't conduct too well. And ordinarily you get nothing. But then with enough spin flip, you should get currents through it. Okay? So if you were to write down that current, it would look something like this. I is equal to a bunch of constants that one can talk about. That's a separate issue. But otherwise, at different energies, and we have these spin flip things that take you, the electrons that flip from here to there. And so you go, there's one process where it is F up times 1 minus F down, which means an upspin electron flips into a downspin and goes down. And there will be a process where it will be F down times 1 minus F up. And there will be constants here, which would be things like density of states in the up channel, density of states in the down channel, etc. Now, the other thing is that should enter here is, of course, this process is facilitated. This is where a up electron, or rather, let's say a red electron becomes blue. But in order for a red electron to turn blue, you must have a blue impurity in the first place. Because the way this spin scattering works is a red electron and a blue impurity, and they flip. So electron becomes blue, but the impurity turns red. Right? Because overall it's conserved. These spin-spin interactions, that's how they work, these exchange interactions. Okay? So in order to facilitate an electron to get from red to blue, what you need to start with is an impurity that is blue. You see? So that's what I'll put here as a capital F, but then it needs to be blue, so down. And in order to facilitate the other process, of course, it will depend on, so this tells me what fraction of impurities happens to be blue, down, impurities. And I use capital F for the impurities, small f for my electrons. And then I have the capital F. So it's like, as I said, integral dE, a bunch of stuff that we don't write, and then times this. Two terms, this minus this. That's it. Okay. This would be the current. Now, question is, would this look like F up minus F down? Because if it is, then the nice thing is, then after you linearize it, it would look like mu up minus mu down. We have done this Taylor series many times. And then it will look like a conductance, essentially.
Why are those capital F's both down?
Thank you. So thanks for finding out. No. This one is up, because you need a up impurity to turn down electron to up. Thanks. Right. So now, as I said, if those impurities are at equilibrium, yes, please.
What's the meaning of impurity for spins? Are they magnetized?
This is paramagnetic impurities, say something like manganese, or I think there are these certain centers in silicon dioxide interfaces which also act as paramagnetic impurities. So any paramagnetic impurity which left to itself is either up or down, gives you an either up spin or a down spin. Right? And at equilibrium, left to itself, it would be half and half, 50-50. That's what I've tried to show there. Half reds, half blues. Right? Half and half. And the point is that if those two things are equal, then you see this minus this, you'll notice this FU, FD cancels out. So when you take this minus this, you just get FU minus FD. Yeah.
It looks a little bit asymmetric. Impurities have just one factor, FD, for example, in the upper line, FD times FU times this parenthesis 1 minus FD. Why you don't do the same, minus capital FD for impurities?
Right, because with the impurities, these are like a, so while we are counting, so you have these electrons that the picture is the electrons are delocalized everywhere. So the electron and you have certain impurities here. Right? And if you have a red impurity, then what it will do is it will allow red electrons to turn. So because I think this difference is partly because of this fact it's delocalized, and also this thing that the impurities are kind of like this Coulomb blockaded situation where it is up or down. So if I have an up impurity, it can always flip to down. It's not like I have to find a down impurity to go to. What I mean by that is when you're thinking of the electrons, it's like it is in an up state and has to find a down state to go to. But the impurity is like it's right here, it just turns over. It's not like you need, if you're this, that must be empty, because there's no way you can be in the doubly occupied one. Right? So that's why there's this asymmetry in what I'm saying. Okay. Now, so the point I was making is that if those two are equal, FD and FU are equal, then yeah, this would just become F up minus F down, and you could visualize it as this additional conductance there, essentially. Spin flip conductance.
Capital F's are just numbers.
Just numbers. Fractional between, I suppose, between 0 and 1. So F up plus F down should be equal to 1. So maybe you should have that clear. Yeah. Yes, please, go ahead.
Many momentum state of particular energy. So if this thing comes in this way, and in which that direction is scattered, current won't depend on the kind of direction, like what is the change of momentum.
Yeah, for low bias, usually just the density of states is good enough. But I'm not sure. In detail to a higher order, they may be important. I'm not sure.
Like what do you do in momentum reduction? 1 minus
Right. Those averages, I am assuming, are hopefully included in m lambda, etc. Right? Those kinds of things. All whatever you see in normal transport, those issues, and these being localized impurities probably would be isotropic in scattering, usually, etc.
So, can an impurity atom interact with more than one electron at one time?
Yeah, I suppose so. It's a So you have one impurity here. So the electron wave function is spread out, and all these impurities sort of facilitate this.
The spin of impurity atom changes, on interaction with one electron. So if we just have one electron and one impurity atom, then the spins will change because of spin conservation. But if you have one impurity atom interacting with multiple electrons, then it's not very necessary that the spin of...
Right, but the basic interaction is still one spin, one impurity, one electron, one impurity. Basic interaction. So, lot of them means those are all individual processes in parallel. But individually, when an electron flips, some spin must flip somewhere. So that the overall, if you look from outside, you tend to see the same spin.
So it's just one-to-one effect.
One-to-one effect. And the assumption is that, the models that people use for spin scattering is that, it is just a basic interaction is one-to-one, but then there would be lots of them. Right? So. Yes.
If we assume that the spin of impurities either spin up or spin down, could that be random interaction?
Yeah, this is where I say that once you get to the, in principle, if things are non-collinear and all that, all kinds of other issues could come in. And here, I was trying to keep clear of that. I said, well, let's assume everything we are talking about is, you just have magnets which are red and blue, whatever you have injected. In that case, that should be enough to understand the basic thing, right? But you're right, that in general, one has to worry about, you could have, of course, in principle, to start with your injection is such that it involves non-collinear things. And that would, then you could ask whether the impurity will start precessing or not. So other issues could come in, right? Which I'm kind of trying to keep clear of here, because there are other conceptual issues I want to focus on, right? Okay. So now the point is this, that when you usually calculate these things, you always assume that the impurity spin is 50-50. But then every time, of course, it flips an electron, there is an impurity spin is, going from red to blue or blue to red. But what is always assumed is that there is something else, nowhere in your Hamiltonian that you haven't written, that always manages to restore them back. It's kind of like the contacts. Again, these contacts, as I said, if this was all, an electron would go from there to there, you'd pick up some negative charge here, pick up some positive charge here, and you'll be done. And then it would be like a capacitor. But what makes it a resistor is the fact that something not in your Hamiltonian, something not quite specified anywhere, continually takes these out and put them back in. That is a very important part of this whole conduction process. Similarly here, those red and blue impurities, you can think of it as a conductance, but what makes it so is the fact that there is something else that continually restores it back to half red, half blue. Otherwise, what would happen is, let's say there was no mechanism at all for doing that. These impurities, there is nothing else they can do. Then what would have happened is, you see, you got lots of ups and lots of downs. So lots of ups are continually trying to become down. Hardly any downs trying to become up. So continually what you're doing is you're taking your impurities and turning them red. Because this is a red electron. It looks around for a blue impurity and turns him red. But nobody is turning reds back to blue. Hardly any. You see, if everything were in equilibrium, then of course there would be as many taking red to blue as blue to red. It would be kept in equilibrium by itself, no problem. But here, because there's a lot more red electrons in there, they're continually doing that. And if it was isolated, what would have happened is, after some time, that left picture would have become like the right picture. All reds. That's it. And at that point, there would be no further scattering either. You see? And then you wouldn't have that spin flip conductance anymore either. This would be gone. You see? And this is the essence, of course, of something called the Overhauser effect. Overhauser is a professor at Purdue, actually, in the physics department. And I mean, this I guess, almost 50 years old now. And with him, of course, this impurities, it didn't involve transport. There, the whole idea was you drive the electron spins out of equilibrium using microwaves. I mean, something else. You don't do it with contacts. In those days, of course, no one had things like this for doing things with current flow. And then the impurities they were considering were the nuclear spins. And the nuclear spins, because the electron spin interacts with the nuclear spins, and the nuclear spins have this property of being extremely isolated from everything else. And so once you turn them, they have hardly any way of getting back. And so the effect can be very striking. And the thing was, when he first proposed it, everyone thought something had to be wrong with that. But it was experimentally demonstrated, and it has lots of practical applications. You'll see, if you do a Google search, you see the Overhauser MRI, OMRI, where in MRI instruments they use this effect and so on. So it has lots of applications and all that. Okay? And in the context of semiconductors also, I think people have seen things like this with nuclear spins. But exactly the same thing you expect with anything really, any impurities, as long as they don't have a good way of relaxing through the surroundings. Right? So up to a point you expect these effects, and my collaborator at Michigan, he did these experiments on gallium arsenide with manganese impurities, and he sees this effect clearly. What he sees is, when you start, you turn on a current, and you get a lot of current because there is this conductance, and then within a microsecond, the current goes down. Goes down because a little later this is gone. It has become may not be as clean as what I've drawn, but because of course it's with real contacts with other issues involved, but the current goes down. That's what he sees very clearly. Okay. So the important point here though is, the point I was trying to make is this essential distinction between a resistor and a capacitor, that what really turns the capacitor into a resistor is forces not specified that continually restore things. That's really, that's in a way something that kind of makes transport generally harder, because these are the issues that are often not all that clear, you see, in the discussion. And this is also a good example. You see, the thing on the left is like a conductance as long as somebody is continually fixing things, continually restoring it back. If you have nothing restoring it back, then it's like a capacitor. After some time, it kind of charges up in a way, if you could say that, right? There was no spin in the beginning. After you're done, you have a lot of spin, all lined up. So there's big spins, as if you kind of charged up a spin capacitor in a way, almost. You've charged it up. Okay? Now, once you have charged it up, though, you have got lots of up spins, and this is now 0. You've charged it up. So, lots of reds. Now the current equation looks like this. And if you now turn off your voltage, you'll actually still get a current. The current will keep flowing. You get a current out of it. Why is that? Well, basically what would happen is, suppose one could say it this way, that you've got, there is all these electrons, the red electrons coming in here, which are trying to become blue. So I guess let me draw that previous picture where I had an energy level E, and you have, say, mu1 is here, mu2 was here, and there were red electrons coming this way, going down, and of course there's also a reverse process. And of course, usually which process dominates depends on Fermi functions. That is how many you have more. But now what has happened is, it's non-reciprocal. You see, this process is facilitated by blue impurities, because a red electron comes in, has to become blue in order to get out. While this process is facilitated by red impurities. And now that you have lots and lots of reds, what happens is, it is as if you have just cut this off. This is going the other way. And so at this point, even if you take off the voltage, it's like the current will be flowing in this direction, kind of against your potential drop. So in principle, once you have turned it red, all red, you could take this and then, I guess, drive a load of some kind with it from that red up to a point, right? And if you think about it, at first you say, well, that's not very puzzling. After all, if I've charged up a capacitor, I can always discharge the capacitor and get some energy out of it. And after some time, it will discharge, go back to the left, sure. But the interesting point here, though, is, that's what I want to make, is that although it's like a capacitor, but there's no energy in that capacitor, though, you see? Because red and blue were perfectly degenerate things. They had exactly the same energy. When you flip from red to blue, no energy is involved. So in that sense, we still have a elastic thing, although it's not an elastic resistor anymore, but I guess it's still elastic, everything we're talking about. No energy exchange is involved. So where exactly did this energy come from? What I mean is, once I've turned it red, I said, and I'll take out the battery and now drive my load. And sure, I'll be able to drive it for a while, which is kind of like discharging the spin capacitor. But where did that energy come from? It didn't come from that spin capacitor, because, as I said, what's on the left and what's on the right have exactly the same energy. That's not where anything came from.
Free energy is different because one is less entropy.
Right. This is what I'm getting at. Exactly. So here then, now if you look at the energy though, energy still must be conserved overall. So whatever you're getting here must have come from somewhere. So if you look at it, what you find then is that, an electron comes in, it takes that much energy from this contact, goes out here, dumps this much into that contact, but it has more coming in, pulls out more coming in than dumping. And so overall, it is taking energy from the contacts and lighting up that light bulb. I mean, your spin capacitor isn't doing anything apart from stopping the reverse process. It's just facilitating one process, but stopping the other one. And in the process, you are actually just taking energy from your contacts and turning it into useful work, essentially. Okay? So this is still true, in a way. But the sum of these, what you are getting from the contacts, this is now a positive number. What I mean is, usually whenever we have talked about this, you may take this much from one contact, dump more into that contact. So overall, the heat you got from the contact is negative, in the sense you dump more than you take, normally. But in this case, actually you are taking more than you dump, overall. So you actually made this guy negative. I'm sorry, they make this guy positive. You're taking more, right? My definition is these things, positive means you're taking it. And so this must be negative, which basically implies that rather than take energy from my battery, I'm actually driving something. Right? So energy is conserved. No problem with that one. So the question is there a problem with this? And this is where I say that, well, this energy conservation, that's what's called the first law of thermodynamics, which everybody understands. I mean, you tell anybody that energy is conserved, you won't get any arguments. The one that raises a lot of discussion is the second law of thermodynamics. And what the second law says is that IQ1 divided by T1 plus IQ2 divided by T2 must be less than 0. Because meaning this is what I want to discuss more, where it comes from, what it involves, that this is the amount of heat you are taking from the source, from one contact. This is the amount of heat you are taking from the other contact. And divided by T, that's like the entropy flow. That is, whenever you take a certain amount of energy from a contact, that is what you, divided by T is the entropy. And this is what I'll discuss more. It's not meant to be clear. Now, if everything is at the same temperature, then what it tells you is that IQ1 plus IQ2 is less than 0. So, if everything is at the same temperature, then you should be giving up more to the surroundings than taking in. Because remember, these guys, when they're positive, it means I'm taking it in. Right? So it has to be less than 0 means I have to give up more than I take in. Right? That's the basic law here. And this is something, of course, you feel instinctively, and it is something that is, again, embodied in this second law. But it raises, it is subtle enough that raises, lots of discussion, lots of literature on this. And ever since it was ever since the 19th century, this has always been discussed a lot. But the basic point is this, that yeah, energy conservation, sure, that we understand. But then, there's always a lot of energy all around you. There's all these molecules running around. There's all this energy. But you cannot build a car that just takes energy from the surroundings and, converts it into mechanical motion, for example. That wouldn't violate the conservation of energy. First law would be fine. You're just taking energy from the air. Sure. Well, what's the problem? But it would violate the second law. Right? Because the second law says that because somehow there is a difference between these two types of energy. The energy of random motion, the energy of randomness all around, and a mechanical directed motion like a car or whatever you're doing with it. And so when you go from left to right, that is something where you're going from something random to something very ordered. So that will never happen spontaneously. But if you're on the right-hand side, then it will happen spontaneously. From that, you can come back to the left-hand side. So it's a one-way process. Unlike most mechanical things, unlike mechanical processes which are all reversible, there's no one-wayness to it. If a planet could go around this way, it could have gone around the other way just as well. That's fine. Mechanical things could go either way. It's this part that is, and that is the point I've been trying to make earlier also, that what makes nanoscale devices somewhat easier to understand is that processes of this type, which actually drive a lot of phenomena in real life. Like most things are actually driven more by this increasing entropy than by mechanical things. Why heat flows from high temperature to low temperature? It's entropy driven. Everything else is really entropy driven. And the biggest problem in all of this transport theory is how to combine the mechanical part with this entropic part, because they're all kind of intertwined usually. And Boltzmann showed how to do it in a classical context. NEGF does that in the quantum context, in the sense it takes the mechanics from Schrodinger and then brings in the irreversible entropic parts through the sigmas in the NEGF. And Boltzmann showed how to do this in the classical context. And this elastic resistor or this nano device context, what I feel the reason it clarifies a lot of these issues, helps you see it all clearly, is because the reversible is here and the irreversible is there. It's kind of all clearly separated. You know exactly what happened. Okay. And so this is the part then, you see, that what you could show is that sure, you can light up a light bulb here, but then after some time, of course, the reds will again become blue. And if you look at what is the maximum energy you could extract from it, you'd find that that number would be this nkt log 2. This takes a little bit of algebra. If you like, we can go over it in the discussion session. But you can actually show it from here, without invoking second law or anything. I could just take this, look at the current, see what is the maximum I could get out of it, and I'll find its nkt log 2. And the justification then would be, so how did we manage to get around the second law? In other words, basically what we're doing here, when you have this right-hand side, is of course actually taking heat from the contacts and lighting up a light bulb. So, which is almost like, as I say, taking energy from your surroundings and running your car. So how are we managing to do that? Well, because the entropy of that impurity system is changing. Because what the second law really says is that the total change in entropy, the total entropy current, So this is the IS that is associated with the impurities. That whole thing must be less than 0. And what is happening is, as far as the impurities is concerned, it is going from reds to half red, half blue. And in the process, of course, the entropy is increasing a lot. Okay. And so, this could still be somewhat positive. I guess what we did here, yeah. So in our problem, this could still be somewhat positive as long as overall it's negative, because the entropy flow there, that part is negative. That is how you justify it. That's okay. No problem with second law, really. It is still following the second law, but this is how it's reconciled here. And this has some similarity, I often say, is this, if you have read the literature, or if you do a Google search, you'll often see this Maxwell's demon. Again, one of the things where lots of literature on it. And what Maxwell had proposed or had pointed out back in, I think, 1850s, around that time, is that's the picture below, that supposing you have a box which has uniform temperature. And so you have all these molecules running around, but then some of them are fast, let's say the red ones, some of them are slow, let's say the blue ones. And if you had this Maxwell's demon, and again, no negative connotations or anything, just somebody who knows about all these velocities and has a way of knowing this, and what he does is he opens and closes a door in between at just the right times. So whenever he sees a blue one coming along, it lets it through to the left, red ones he lets them through to the right. And so after some time, what will happen is all the red ones will be on the right and all the blue ones will be on the left. And so the left-hand side will be colder and the right-hand side will be hotter. And of course, once you have a temperature difference, you could then use that as a thermoelectric to, drive other things. You could do things out of it, right? So in principle, as long as he can be opening and closing that door without spending any energy, the argument was, look, you could violate the second law, essentially. That was the argument. And so the question is, what's wrong with it? And this is what people have argued a lot. And in a way, what's up here, you could think of as Maxwell's demon, who lets electrons flow in one direction and not the other. That's basically what it did. With a red, you cut off one group of things. That's it. And that's how it's supposed to be working. And basically, of course, the resolution of all this is that the Maxwell's demon, sure, if he started out energetic and ready to do things, he could do this, but after some time, just the process of doing it would basically drain him. Basically, if he started out like all reds, eventually it would become that. That's the essential point usually. Okay? Now, of course, in the modern context, there are all kinds of other issues now that people are worrying about, things like entanglement and things like what quantum mechanics adds to this picture, etc. But those are separate issues I'm not going into. Just classically, I'd say this gives you kind of an electronic Maxwell's demon. Okay. Now, this to me is kind of brings out the basic problem here. And that's what I want to talk about, that when you try to include inelastic processes, into any description, the problem you have is, okay, let's say just something simple like a hydrogen atom. You've got two levels. So 1s, 2p level. And what we know is that if you put an electron here, it will come down. If you have an electron here, it won't go up by itself. And so the implication always is, when we always say this, oh yeah, given any system left to itself, it always goes to its lowest energy state. Okay? And doesn't usually raise much questions, especially by the time you're a graduate student, you know that, if you question that, you get people annoyed. Right? So you usually don't bring that up. But with beginning students, I do still often have that question, that I say, why does it always go to the lowest energy state, really? Necessarily. And as soon as you try to build a transport model, of course, you run into this, because, especially quantum transport model, because anything you put in, these Hamiltonians are all Hermitian. If there's a HMN, there's a HNM. So whatever you do, anything that takes you down will also take you up. That's a bit, right? All mechanical things, as I said, they tend to be reversible. No matter how you do it, you usually have that. And so you can't even describe this basic fact we all know, that namely, left to itself, it will go to its lowest energy state. And this is where I guess, again, all this discussed many places. Here's the clearest thing I've seen is, I think, in Feynman's statistical mechanics. I think he almost, in the first couple of pages, he explains this. And what he says, I think, amounts to something like this. He says that, look, in an isolated system, if I had put an electron there, it would have just stayed there by itself. The reason it is coming down at all is because it is interacting with the surroundings. And the surroundings you could view as, if this is energy, there's a density of states of the surroundings. And when I talk of density of states, is then this entire complicated object that I call reservoir, which could involve millions of electrons. Question is in how many ways can that state, that reservoir, take energy from your surroundings? And he argues that, well, if you looked at the density of states, all common reservoirs would have an increasing density of states. So low energies it's here, higher energies it's somewhere up there. And so let us say an electron is here and the reservoir is there. When the electron comes down, energy is conserved. So electron is now here and the reservoir is now over there. So if this energy exchange involved is epsilon, then the reservoir, if it was initially E0, it will now be E0 plus epsilon. Okay. And the argument then is, so why is it easier to go down than go up? Well, because, you see, when you are going down, you're going this way. I mean, the reservoir is going this way. And all normal reservoirs will have a lot more states up here than here. So you might have, say, 20 states here, and you might have 20,000 states there. So although you're looking at it and saying, well, you've got one state here and one state I'm going up and down, it is almost as if, you see, this one corresponds to 20,000 states, and this one corresponds to 20 states. So even if the basic rates are equal, the point is it's much more likely to be going down. That's the basic argument here. Okay? And so any normal reservoir then will have this. And it's kind of good to think about these things because, as you go to nanoscale things, there's no guarantee that, if you're creative, you might be able to get around some of these things. So it's actually all worth thinking about clearly. Okay? Now, but usually with all normal reservoirs, this is the case. Okay? And so what you can write then is, so the net result of all this is, with any reservoir, like I mentioned there, it is easier to give up energy than to extract energy from it. Because whenever you give up energy, you're kind of increasing the number of states. That's like going to the half red, half blue thing. And this is like the full red thing. So whenever you give up energy, you always have a lot more states to go into. And that is why there's always this ratio that, I think what I wrote there, let me write it. So the probability that what the energy it takes, the probability of giving up an amount of energy epsilon divided by the probability of taking an energy epsilon. So when I write plus epsilon, I mean taking. When I write minus epsilon, it means giving up. Okay, that's what I've done there. And that will be equal to the density of states. I guess I wrote it as W there, I think. The same thing. I really mean density of states. W of E plus epsilon 0. I'm sorry, E0 plus epsilon. Okay. And then this famous Boltzmann's relation, this is this S equals K log W. That was the definition of actually, Boltzmann's constant, this KT, the K that you see everywhere. And S is equal to K log W. So W is this density of states, how many states you have, and logarithm of that. And so W is equal to e to the power s over k. And so that becomes e to the power s E0 plus epsilon minus s E0 over k. Right? So what I've done is, instead of W, I've written exponential s over k. Write this. And then again, big things, I can use this Taylor series expansion again. So you write it as e to the power ds dE times epsilon and then over k. And the thermodynamic definition of temperature is this derivative of the entropy with respect to energy, I mean inverse of that. So usually this definition is so that's how this becomes epsilon over k. So this is the basic point, that these entropic forces will always be such that whenever you're looking at a reservoir in equilibrium, a contact in equilibrium, the giving energy to it will always be easier than taking energy from it, and by that ratio, exponential epsilon over kT. And this is what drives the flow of heat, for example. So the argument you usually have is, okay, let's say this is E, this is entropy. So if you have something at high temperature, that is, this is very high, then ds dE will be almost zero. So a high temperature thing will have a, where you can change E a lot, S won't change much. Whereas if you have, this is high temperature. And if it's low temperature, it will be like this. And supposing you want to have transfer some amount of energy from one to the other. So from the high, let's say we take out some energy. So it goes from here to there. That much energy we take out. And so the low one goes that way. So you see the high one hasn't changed entropy much, but low one has increased a lot. And so overall entropy has increased. So that's the way heat will flow. On the other hand, if you tried to go the other way, then what would have happened is you'd have lost a lot of entropy but gained very little, etc. So the point is, these are things you always see in thermodynamics text, statistical mechanics texts, and the point I'm trying to remind you is that lots of things in real life are not driven by mechanical forces that you can put into a Hamiltonian, but driven by entropic forces. And if you have pure Hamiltonian, all you have is a capacitor. Finally, things of this type are involved to turn the capacitor into a resistor, really. And they need to be included somehow in this whole discussion, in any transport theory, you see. And in general, then, what happens is, if you think of a process, let's say, like, one little thing I should, what I want to prove next is, what I can say, one of the questions that you could have is the following, that, okay, this second law, which I guess I erased it, so let me write it up again here. The second law, which is IQ1 plus over T1, IQ2 over T2, plus any other entropy issues, all that always has to be less than 0. Again, because the way I defined it, this is the amount of heat you are taking from a reservoir, and whenever you take heat from a reservoir, you lower its entropy. So, yeah, so this has to be negative because overall you must be increasing the entropy. That was the argument. And what I said is that when it comes to that spin system, the entropy is of course very clearly increasing when you go from right to left. But here, so the way usually for a reservoir the entropy is calculated is that if you give a certain amount of energy to it, the entropy changes by that energy divided by the temperature, E over T. Right? So that's what I said this, because ds dE, that's like 1 over T. But that is true only of things at equilibrium. So what I mean is, you couldn't use that idea to figure out how much the entropy changed from right to left, because that right thing is out of equilibrium. All these ups and downs all have the same energy. To have them all filled, that's a way out of equilibrium situation really. At equilibrium, they would have all been 50-50. But this is a case where you can get the entropy easily by just going to the basic definition of entropy, namely S equals K log W. So the whole idea is, if you have n impurities, how many ways can they all be red? Well, there's only one way. They're all red. How many ways can they be half red and half blue? Or how many ways there can be anything else? That's where approximately it would be 2 to the power n. Because the idea being each one can be red or blue. And so overall there is this 2 to the power n states. So you have to subtract out the red from that, but then this is a big number, I don't worry about that. And then this becomes like nk log 2. Okay? But so that's how you'd calculate the entropy associated with that. And in general, when you have non-equilibrium problems, of course, exactly how you should define entropy and all, that people argue about, that's still discussed. It's not necessarily all that clear. Whereas when it's equilibrium things, then it's clear what exactly you mean by entropy. How much the entropy changes for a given energy, etc. That's all settled then, right? Now, then where does the second law come from? Or what I mean by that is, when I'm building a model for a device and I'm trying to calculate currents and all that, how do I make sure that I won't be calculating anything that would be violating the second law necessarily? You see, because everything we have done so far, if you are using this model and you're doing, say, thermoelectrics where you're taking a certain amount of heat from here, dumping it over there because there's a temperature difference and all that. If you use the formulas we have discussed, there will be no problem with second law. Okay? But the question is, how can you be sure? And the point I want to make is that is always ensured as long as this is correct. What I mean by that is, as long as whatever contacts you have the property that when you take energy from it and when you give energy to it, the ratio of those two happening is e to the power epsilon over kt. As long as this is true, you won't have any problems with second law. Okay? Now, this is the one where if you're doing a Boltzmann equation, for example, when you write scattering rates, you always try to make sure that S12 and S21 have that ratio between them, for example. The corresponding thing in NEGF is a little more subtle, because there also phases are involved, in the sense that electron kind of becomes like this correlation matrix, etc. But NEGF, again, if you follow the prescription right, this would be ensured. So you'd automatically have this second law conserved. But then if you make approximations or things where you're not necessarily following the exact prescriptions, then you have to be careful, because otherwise you may be doing things that are really not physical. Now, why is this related to that? Well, it's kind of like this. Supposing we have this simple elastic channel here, which is operating with multiple reservoirs. So you have one reservoir here with some mu1, T1. This is some reservoir here, mu2, T2, etc. And if you take a certain amount of energy from here, say E1, and let's say I consider one process where you take an amount of energy E1 from here and an amount of energy E2 from there. And the probability of that happening is this FE1 times FE2. That is, a process like that will have a rate that will be determined by this F that tells you how easy it is to take energy from this, or take energy from that. Now the point is, corresponding to that, there will always be a reverse process where you give up energies to the, and those would be like f of minus E1 and f of minus E2. And the point I'm trying to make is, in order for this process to be the dominant thing, the one that is actually happening, because you could overall say that the rate at which this will happen is this minus the opposite process. This ratio must be greater than 1. 41. And what that means is, you see, FE1, that is like e to the power minus E1 over KT. Then it's e to the power minus E2 over KT. All that is greater than 1. Sorry, or T1, T2. And so, E1 over T1 plus E2 over T2 should be less than 0. In order for that process to be happening. And this is if you are just taking some energy. Now, if actually an electron is transferred, then of course, while electron is transferred, another one comes in here, because it's an open system with a certain chemical potential. So the actual energy you take from that contact is like E1 minus mu1. So if you had done it that way, then you would have come up with E1 minus mu1 plus E2 minus mu2, etc. And to some extent, that's the second law, right? But all I'm trying to show is that as long as your model, the model that you're using includes this in how you define your probabilities, you would be in keeping with the second law. That's not something you need to think about separately. And all this is kind of important again because, as you know, in the future, firstly, lots of concepts may need to be revisited as we go along. That is, this whole idea of entropy of reservoirs, because when you have small reservoirs, what happens? Because normally, one would have said that a spin system is like a reservoir. You could treat it as a reservoir. It's always maintained half and half. Well, not really. As I said, nuclear spins deviate significantly. And then there can be all kinds of other things one can think about, for example. And then there is this general question of energy conversion, waste heat conversion. That is, how do you build devices that can just take energy from the surroundings and convert it into useful work? Or something that can take energy from your body and do useful work, for example. And all these involve these general basic principles again. See? All that. And so it's important to be clear on all this, because these are all concepts that took many years, hundreds of years essentially to clarify, and lots of discussion. And even now you see lots of discussions about it. And usually, of course, the discussions are a lot more convoluted because, again, the two types of processes, namely the mechanical ones and the entropic ones, are kind of mixed up, usually. Usually it's not this clean. It's not like this is mechanical and then it's all entropic. It's like everything's happening, all mixed up in a proper way. And then so anytime you do a transport theory, when you're trying to put in, so this elastic resistor model that I described to you, what we did was we said, well, all the entropic stuff is here, and I don't have to worry too much about the details of this at all. How do I take care of it? I say, well, this is a big contact. You always maintain it at equilibrium with F1 and maintain this at equilibrium with F2. And those are, of course, the functions from equilibrium statistical mechanics, which satisfy these principles. So when you're trying to write down the rate at which the electron can get out there or come back in, they obey the correct ratio. The ratio needed for second law and all that. So there's no problem. It's automatically taken care of. And in the middle, it's all just pure mechanical motion, described by a Hamiltonian, described by Newton's law, whatever you like. See? And that's how it separates out cleanly and makes sure that overall it will be consistent. Anytime you want to put in the inelastic processes in here, well, that's then, Boltzmann gives you a general prescription for doing it. And of course, all scattering rates would obey that property. And then in NEGF again, corresponding thing, but quantum. That is what it will usually give you. Right. Now, to finish up then, the points just to go back, this was the outline of the things we went through. Now, in these lectures, what I tried to stress more was the concepts rather than the actual, as I said, calculating and understanding are often different, right? And those have to be done together, but these are somewhat different things. Now, if you're looking for, specific problems, so you're trying to learn how to calculate certain things, then I'd recommend, for the semi-classical, the simplest thing I usually recommend is what I call the point channel model. That is a device where you treat the entire channel as a single point with a certain potential, and how you do the calculation self-consistently. And when you do that, you can calculate the current voltage characteristics. That's reasonably close to real calculations on MOS devices, actually. But it gives you a very good feeling for how electrostatics controls things, how different parameters here would change the current voltage characteristics. Now, if you're trying to learn quantum transport, then as I mentioned, those are the basic equations. But the two examples I usually recommend then are, I don't know if I have it here. Oh. So the two examples I usually recommend are this localization problem, which means there's 1D wire with impurities, and then the 2D problem, which is the quantum conductance of a 2D wire and quantum Hall effect, etc. So those examples usually give you a pretty good picture of things in an applied. So I'd say if you're trying to learn the methods for calculating, those would be the two I'd recommend. And these are things where, I have if you send me an email, I can easily send you the MATLAB codes I have. These are things that I use for homework problems in the courses we have here. And we have an undergraduate course and a graduate course on the subject, and we have various homework problems, which basically are these, right? You see. So those, anytime, if any of you are interested, if you send me email, I'd be very glad to just send it to you. Okay? But what I wanted to stress more was this conceptual aspects of this, and that is where I said that, there are all kinds, because whenever we discuss these things, people say that, well, we need to learn more quantum mechanics. And that's kind of true, but I think what is much more important is to appreciate statistical mechanics. I mean, quantum mechanics, I'm not downplaying it at all, but as you can see, there are lots of things here that you can understand within a semi-classical picture itself. And that is because a lot of these subtle interference effects tend to get washed away because of especially if you're doing it at room temperature. A lot of these subtle things wash away. One of the things that, however, is observed at room temperature these days and persists is the spin. Because spin is one thing where, again, up to a point you can think classically, just as red and blue, but not quite, because whenever you have non-collinear spins, you need the quantum aspect of it, as I tried to point out. Those off-diagonal terms kind of matter, and you have to have a way of thinking about it, right? And this part of it, you could say, involves quantum transport in a way. Otherwise, I'd say the quantum models, well, if tunneling is involved, then I think quantum models are needed, usually. So, but overall, though, I feel that in transport, what is much more important is to appreciate the statistical mechanics part of it. And there, of course, what we need is non-equilibrium statistical mechanics. But that, as I said, is much less understood and relatively few courses or books on compared to equilibrium statistical mechanics. So what you can, of course, take standard courses on and learn very well is equilibrium statistical mechanics. Right? And again, that is a very profound subject that took hundreds of years to really clarify. Right? And when it comes to non-equilibrium, as I said, there is all these issues that it's not, there are all kinds of models, all kinds of things that people are looking at. And as I said, with small devices, if anything, I feel it clarifies the concepts. You can actually understand things much better than the non-equilibrium statistical mechanics of big systems. That's relatively much more complicated, really. Okay. So we have this discussion session today at 3:30. So if you please, pass on your questions ahead of time if you can, or raise them at this point. And I'd like to, answer any questions that you may have on I guess everything that we have discussed here. Okay. And yeah, thank you. Something like this. I is equal to a bunch of constants that one can talk about. That's a separate issue. But otherwise, at different energies, and we have these spin flip things that take you, the electrons that flip from here to there. And so you go, there's one process where it is F up times 1 minus F down, which means an upspin electron flips into a downspin and goes down. And there will be a process where it will be F down times 1 minus F up. And there will be constants here, which would be things like density of states in the up channel, density of states in the down channel, etc. Now, the other thing is that should enter here is, of course, this process is facilitated. This is where a up electron, or rather, let's say a red electron becomes blue. But in order for a red electron to turn blue, you must have a blue impurity in the first place. Because the way this spin scattering works is a red electron and a blue impurity, and they flip. So electron becomes blue, but the impurity turns red. Right? Because overall it's conserved. These spin-spin interactions, that's how they work, these exchange interactions. Okay? So in order to facilitate an electron to get from red to blue, what you need to start with is an impurity that is blue. You see? So that's what I'll put here as a capital F, but then it needs to be blue, so down. And in order to facilitate the other process, of course, it will depend on, so just the spin valve we discussed before, but now let's assume that the channel has lots of these paramagnetic impurities, manganese impurities. So what do these impurities do? Well, they give you lots of spin flip, basically. Why? Because there are all these impurities which can be either in an up state or in a down state. So left to themselves, there's one electron in there, there's an up state or a down state, but you cannot put two electrons in it because of this kind of Coulomb blockade type situation that takes too much charging energy to have two in there. But it could be either this or that. And so as long as the chemical potential is in a certain regime, this is the state it would be. It would either be this or that. And so there would always be an unbalanced spin. It would be, so these are what are called paramagnetic impurities. And there are lots of defects in different semiconductors and in gallium arsenide. The experiments we have done on this, those involve manganese impurities. So there are different things that would give you this kind of a situation. And that's what I've indicated there as those red and blue dots. And I say red and blue because you see half of them are upspin, half of them are downspin. Left to themselves, there's no energy difference. It could be in either place, and left to themselves, it will be 50-50. So that's what I've shown there. Now, how would you model that? Well, in our resistor style model, that would appear as a major, like a spin flip conductance here. That basically kind of shorts the two channels together. In a sense, if you have a lot more ups, it will send a spin flip current and do it. And of course, normally if you are building a spin valve, no one in his right mind would do this.
NanoHUB.org. You can follow along with this presentation using printed slides from the NanoHUB. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
So in the last lecture, we talked about spin, and what I'd like to do is continue, but touch on a slightly different aspect. Now with spin, the point I was trying to get across is that there is a very different issues involved when you get to non-collinear spins and collinear spins, right? Because collinear spins you can think just as red and blue. And so what I'll be talking about now in this lecture, you could more or less, basically we'll assume collinear spins. So in that sense, the extra complication due to non-collinear, those issues are not involved. But the way it is a little more complicated is it kind of involves the two topics together, namely heat flow and spin flow. What I mean by that, like the last lecture, yesterday I talked about heat flow, and then today we talked about spin. And here I kind of consider the two things together and some of the very important issues that one should be aware of. Okay, and that's why I kind of wrote here, again for your reference, the equations we had for heat flow, if you remember. The way we talked about this was that, well, if you have these electrons, and for this discussion, let's say some level here. And as we discussed, whenever an electron goes through, and they go to great lengths to avoid this. You're trying to get rid of all magnetic impurities, right? But here I'm really trying to make a conceptual point, which is what I'm saying, let's do. So let's say we got lots of these impurities. And the way you then model it often is you think that, well, the impurities are half and half red, half blue. And so this is how I model it. That's the resistor. And the way you often calculate, how do you calculate the current in this case? Well, for this discussion, let's assume we have very good contacts. So in a way, as if this is just open. So very good spintronic contacts. So only these reds come in, blues get out there. That's it. And so, and these are anti-parallel, of course. I'm taking the anti-parallel configuration, okay, for this discussion. And so what would happen then is, you see, if you didn't have this spin flip thing, there would be no current at all in such a circuit, because this is the anti-parallel thing. This would be like having infinite magnetoresistance. Parallel, great conduction, anti-parallel doesn't work at all. Okay. But then, as soon as you allow some spin flips here, then current can flow like this. So the question is, how would you calculate that current? Okay? Because here, this approach isn't quite getting you there, because here, that is based on conduction through up channel, conduction through down channel. But here it is different. It's like up channel by itself doesn't conduct too well. Down channel by itself doesn't conduct too well. And ordinarily you get nothing. But then with enough spin flip, you should get currents through it. Okay? So if you were to write down that current, it would look like elastic resistor model. You can calculate the current from this equation. We have written this conductance in various forms. One of those is this one. So number of modes, mean free path, etc. And if you wanted to write heat current, it almost follows from here. Only thing is, instead of the Q, you have to put in this E minus mu. That was the idea. And the idea being that when an electron comes in from here, and if you think of an electron going through an energy channel at some energy E, then the amount of what the electron that actually comes into the contact has an energy mu1. What is here is E, and it essentially picks up that much energy from the contact. So that's how you look at the heat current. And then what it dumps there. And if you looked at the overall heat current, the conservation of energy would be something like this. This is the heat you take from, the way I'm defining my heat currents is that if it's positive, it means it's coming from the contacts. So this is what you get from the contacts. This is what you get from the IQ2. And this is the part that's coming from the battery, etc. Right? I think this is what we had discussed. Now, we'll come back to this. Now, getting back then to the spin valve, I want to use it as sort of as an example to show that there are problems where even in a nanoscale device, you may not be able to write the current this way as F1 minus F2 times something. You know, this was kind of a central thing, that no matter what, you write it as F1 minus F2 times something, and that something then we can talk about what it looks like in different conditions, right? Now, so the example we are considering is the following.